Hello student, very good morning to all of you. I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the minor synthesis of minus pentenomycin. Do you remember what are the reagents used while synthesizing that minus pentenomycin? Let us recall those collective reagents used for the synthesis of pentenomycin. Number one is used as a methane, nitromethane is used over there for introduction of that in presence of the base, and we will get as a proper reagent introduced into that molecule. And then another one we have used as alkaline potassium permanganate, then sodium borohydride. As we know that potassium permanganate here used as an oxidizing reagent, what it will do, it will oxidize that CH2 nitro group into as a carboxylic group, and then selectively treated with the sodium borohydride used as a reducing reagent for the aldehyde is converted into as a primary alcohol. Then another one used as a benzyl bromide in presence of sodium hydride as a base, and the DMF is used as a solvent, so that we will get as a protection of that alcohol. Then hydrolysis, it is used for the deprotection of that 1,2-diol, then NaIO4, then sodium borohydride. NaIO4 is used as an oxidative cleavage of that diol, and we are getting as aldehyde, and that further treated with sodium borohydride, and we obtain the alcohol over there. Then TSCl in presence of the pyridine, it is used as a protection of the alcohol again. Then Me2CO Me2 in presence of H plus, it is also used as a selectively for the protection of that 1,2-diol. Then tertiary butoxide is used as a base, strong base, and then finally as a lipase deacetylation is used, and we are getting as a minus pentenomycin. These are the things we have discussed yesterday. What we are going to learn today, look at the board what is written over there, that I think today's lecture is a final lecture for the Chiron on the Chiron approach, because we are synthesizing as there are the 6 target molecules, and as we know that this last one, 6th one, is the name of that target molecule is a minus Cicamic acid. And as we know that target molecule means what? The molecule whose synthesis being planned is called as a target molecule. And the first one, that is a retrosynthetic analysis. Retrosynthetic analysis, it is a term used in the retrosynthesis, and as we know that retrosynthesis means what? An imaginary but logical reverse chemical reaction which help us to reach the reactant starting from the target molecule is known as retrosynthesis. And retrosynthetic analysis means what? The process of breaking down the target molecule into a convenient starting material using disconnection and FGI is known as retrosynthetic analysis. And in the retrosynthetic analysis, 2 important terms are involved. Number one is a disconnection, another one is a FGI. Again, disconnection means what? An analytical operation which break a bond and convert a molecule into a possible starting material is known as a disconnection. And FGI means what? This is another term involved in the retrosynthetic analysis. One of the functional group is converted into another functional group, so that disconnection becomes as a possible. So this is all these things. Now moving toward this one is the Cicamic acid. Well, this is one of the natural product we are going to synthesize today. So how do you synthesize it? Let us see some of the introductory part about this one. And this important biosynthetic intermediate have been prepared in optically pure form from D-arabinose. D-arabinose, it is one of the, what we can call it as a chiral precursor. Chiral precursor nothing but as a chiral template, or which is a starting material is we are going to use here for the synthesis of the Cicamic acid. Examination of the triol structure common to the two targets reveals a D-arabino configuration or D-lagzole, and thus if an extra carbon atom can be inserted between the two extremities of a pentytol derivative, and then there would result the trihexane derivatives, cyclohexane skeleton of the target compound, and thus D-arabinose was converted to the tribenzylated aditol by standard procedure. Then using an intriguing reaction, and it was converted into the Wittig reagent. The product is obtained based on protection studies in Weizmann laboratory, and this reaction provide an unusual approach to the synthesis of the cyclohexanone derivatives. And from aditols and treatment of this product with formaldehyde gave the exocyclic methylene derivative, and which was dehydrogenated, note method here, and oxidized to the known ketone product previously prepared by Greaves. The steps leading to minus Cicamic acid followed procedure reported in the literature. Note, however, that the POCl3 procedure led stereospecifically to the Cicamic acid, and synthesis of racemic optically active Cicamic acid are available by the other route also. And chemical and biochemical conversion of carbohydrate derivative into cyclohexane derivatives related to the Cicamic acid have been reported. Now let us begin with the first one, retrosynthetic analysis. That is a half part we are talking here. Now, as we know that the target molecule, the structure of the Cicamic acid, at the beginning we already seen that one. This is the structure of Cicamic acid, COOH, C double bond OH, and now toward the double bond there will be these two hydroxy group, they are above the plane, and other side one hydroxy is below the plane. This is the structure of Cicamic acid. This is alpha beta unsaturated carboxylic group, and now you can do the FGI, functional group interconversion. This is our target molecule, and as we know that target molecule means what, whose synthesis being planned is called as a target molecule. FGI means what, functional group interconversion. One of the functional group is converted into another functional group, so that this connection becomes as a possible, and therefore we are this carboxylic group we are converting into this one cyanide group, C triple bond N, and other thing they are remains as it is OH, these two OH are above the plane, another OH is below the plane. After that again do the FGI. After doing as a FGI, what you are going to get over here, this one, this carbon-carbon double bond, we can convert into, we can bring here cyanide group and here is a hydroxy group, other group OH, and this OH they are remains as it is, and OH. So this we are doing the retrosynthetic analysis by using, this is a disconnection arrow and FGI is written over on it. And next one, FGI functional group interconversion. After doing that, what here, if a carbonyl group is there, then we can get as a cyanohydrin type of the derivative, right? And now this is a hydroxy group OH over there. Here OH, another OH is below the plane. Only just this carboxyl group we can obtain this type of the cyanohydrin derivative. And after that you can do again as a FGI functional group interconversion. This carboxyl this group can be obtained from this one. If there is a exocyclic carbon-carbon double bonds are there, this type of the double bond we can bring over here by using as a Wittig approach, and therefore it is written over there dash OH, right? And after that again do the FGI functional group interconversion. What you are going to get over here, now we are keeping all these things as it is here. Similarly, C double bond only we are protecting this with the benzylic chloride, benzyl group OBN. Then here also same OBN and then dash OBN. What we did, this is a functional group interconversion, and as we know that functional group interconversion means what? One functional group is converted into another functional group so that this connection becomes as a possible, and that's why we are doing this one. And this double bond can be obtained by using as a Wittig approach over here, this OBN, then again other part OBN remains as it is, this OBN also remain as it is, their double bond PH3 here you can put as a triphenyl, this type of the Wittig reagent, and that Wittig reagent further we can do the functional group interconversion. How we can get this one? So you will get this type of the compound over there, OTS and OTS, then other part remains as it is, OBN, another one again as a OBN, here dash OBN. This is a thing remains as it is. Again do the FGI functional group interconversion. Again functional group interconversion OTS, we can get here the structure is like this OH, if alcohol is there OH, and here we can get as a OBN as it is, OBN, then again as a OBN dash OBN, benzyl group. And now this can be obtained from FGI functional group interconversion, and this can be obtained from the arabinose. So like this, here is an oxygen atom, 6-membered ring, here we can put as a OH hydroxy group, then here also as a OH, this side also as a OH, here also as a HO and dash OH, and this is the name of this compound D-arabinose. This is a D-arabinose, and D-arabinose is the starting material used for the synthesis of the, it is present in open chain as well as in the what we can call it in the cyclic form. So this is a retrosynthetic analysis. If you observe this reaction carefully, how the retrosynthesis can be done, which is shown here like this. So this carboxylic, look at here, carboxylic group, if there is a cyanide group are there, we are, while doing as a retrosynthetic analysis, always use as a Chiron approach, means we are going to reach to the starting material from that, and starting material, and we know that the four are the precursor, are the chiral precursor. One is a carbohydrate type of the carbohydrate type of the symmetry. Second one is alpha amino acids or carboxylic acid or the terpene. These are the things you have to keep in mind while synthesizing. But most of the whatever 6 compound we are learning, all are from the one is I think in one case we have everywhere the carbohydrate symmetry, and carbohydrate type of the symmetry, in some cases it is apparent means we can clearly see the carbon framework over there. Sometimes it is a partially hidden carbohydrate type of the symmetry, and sometimes it is a completely hidden, but you have to find out by doing as a retrosynthetic strategy, and we are arriving over there. Look, if you see over there from this compound, this is just hydrolysis, you will get as a carboxylic acid, and here this carbon-carbon double just as a dehydrogenation reaction, and we will get as a this type of the double bond can be obtained just by heating. You will get as a double bond over there, and this group cyanohydrin derivative can be obtained from the ketone like this with the hydrogen cyanide like this, and this double bond, exocyclic double bond, preferentially or exclusively bringing by using as a Wittig reagent. So this is the functional group, here only as a protection of that hydroxy group. Here the Wittig reagent can be obtained by this one, then OTS is there, and then we will get as this is a arabinose. This is a retrosynthetic analysis. Now let us start as a half part remaining, that one. What is that? That is a synthesis. Now we are going to start as a synthesis. How do you synthesize this one? Let us see the synthesis of that cicamic acid. It is one of the, or it is a last molecule of this contain. Now see the synthesis of this. Let us see synthesis. Second half part is a synthesis, right? Synthesis. As we know that the starting material is arabinose. We know that this one arabinose. Here oxygen atom, 6-membered ring. Here is a hydroxy group. Here this hydroxy group above the plane, this hydroxy group also above the plane, and one of the hydroxy group is below the plane. This is a D-arabinose, and this further treated with Rane nickel, right? Rane nickel, that is a H2O, that is a reducing reagent. What it will do? It will reduce this group, and we are going to get the product here, this one, OH, hydroxy group on this side, and here 3 hydroxy group, they are on the right hand side. So this type of the compound we are getting, and now this further treated with pyridine in presence of TrCl, or we can use as a TSCl, tosyl chloride, anything we can use. And if you use it, how do you get? You are going to get the product. Here let me draw first clearly. Here OTS, and here also as a OTS. Other part here hydroxy group, which is above the plane. Here also as a above the plane, and here is a below the plane. 3 hydroxy groups are there. They are this one. They are shown like this, right? And now after that you can treat this in presence of benzyl chloride and KOH in presence of base. What is going to happen? All these 3 hydroxy group get protected and we are going to get the product here like this, OTS, and here remains as a OBN, this one also as a OBN, and this one is below the plane OBN, right? This is the product we are getting over there. And after that, you treat this compound with aqueous acetic acid. This further treated with aqueous acetic acid. So OTS group get converted into this one OH. Other thing remains as it is, OBN, then OBN, and then OBN. These three group remains as it is, and then this will be further treated with what is that? With that pyridine TS, pyridine in presence of pyridine, again pyridine in presence of TSCl, tosyl chloride. Again this group get protected again. This group further get protected. What we have? Okay, OH, then protected, let it be. Then we are going to get here OTS, then OTS, here OTS. There is no need to as a D protection here, so directly we can write here. Don't do that one. Here we can use as a further you can use as a Wittig reagent, that is PH3P double bond CH2, Wittig reagent. What it will do? It will remove this OTS, 1TS controlled reaction it is, and here PH3, that is a compound we are going to get over there, and other thing remains as it is, OBN, here also as a OBN, another one here dash OBN, that is a thing we have got there. And now this one further, this proton get abstracted by OTS, tosyl group like this, and there will be a formation of negative charge, so that you are going to get the product. This one OTS remains as it is, here PH3 minus charge over there, and other thing remains as it is, OBN, and this also as a OBN, they are as it is, and this OBN is below the plane. Now that carbanion is now is what we can call it is a stable one. It is going to attack on this OTS, and this get removed. We are going to get formation of the 6-membered ring like this. Here we are going to get this one PH3 over there, and PPH3 here is a positive charge, right? Here will be a positive charge. This positive charge remains as it is, positive charge, and then here this OBN, this one is a OBN as it is, and this one OBN also as it is. Now in the next case, what is going to happen? This further OTS, here is a one of the proton, OTS will pick up the proton, and it can form as a double bond over there, and you are going to get this one formation of PH3, and this one remains as OBN, this OBN as it is, and then dash OBN, right? These things remains as it is, and after that we can treat this compound with the formaldehyde C double bond OH H, and how it will react with this compound, and you are going to get another thing like this. Here is a PH3, then, or for sake of convenience you can write PH3 over there, O, and this type of the butane ring is formed over there, and this one OBN, because this is going to attack at this, and this is going to attack on P, and so that we are going to get this type of the compound. Then OBN dash 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 OBN. Now this the driving force of opening as a 4-membered ring, this form as a double bond over there, and this form as a double bond with that phosphorus oxygen driving force, because phosphorus has a great affinity toward the oxygen, and that's why stable bond is formed, and where we are going to get over here this type of the compound like this. Here double bond comes here, and this OBN remains as it is, and another OBN also remains as it is. This is also OBN remains as it is, and further this compound is treated with sodium in presence of liquor ammonia. So what it will do? This will deprotect the benzyl group, and you are going to get the product like this double bond here OH, this OH dash 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 OH over there, right? And after that it is treated with pyridine in presence of pyridine and acetic anhydride. What is going to happen? All these hydroxy group get benzylated, and we are get protected, and we are going to get here the product OAC, then again as a OAC dash 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 OAC like this, and further it is treated with NaIO4 or OSO4 osmium tetroxide. What it will do? It will break the bond, carbon-carbon double bond, and you are going to get into as a fragmentation, and means here you are going to as a carbonyl group over there, and there OAC, here again is a OAC, and dash 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 OEC, and after that you can treat this compound with sodium, what we can call it as a hydrogen cyanide, and you will get as a cyanohydrin derivatives, and the derivatives are like this CnHO. Then what is that? Other thing remains as it OAC. This is also remains as OAC dash 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 OAC, and this compound further treated with, I am writing now here, treated with that compound treated with the pyridine in presence of POCl3. Pyridine in presence of POCl3. What it gives? It bringing that dehydration reaction takes place, and you are going to get here Cn double bond. Other thing remains as it is OAC, and here also as a OAC dash dash OAC. This is a product we are getting, and further you can treat with hydrolysis with sodium hydroxide in presence of H2O. What it will happen? This is converted into acid, and they get deprotected, and we are going to get our target molecule COOH, which is a Cicamic HO. This is a Cicamic acid OH dash 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 OH. Remember, this is a Cicamic acid. In this way we have got over here. And what are the collective reagents we have employed or used in this reaction? Let us see collectively. Here we have used as a Rane nickel in presence Rane nickel, which will reduce the particular group, that ring open. Then TrCl in presence of pyridine or TsCl in presence of pyridine, that is used as a protecting group. Benzyl chloride in presence of KOH, also used for the protection of the hydroxy group. Then TsCl then Wittig reagent we have used, formaldehyde we have used, then sodium in presence of liquor ammonia we have used, then sodium oxide in presence of methanol, or sodium iodide osmium tetroxide is used to break that carbon-carbon double bond, and we are getting ketone. Then we use as a hydrogen cyanide, then HBr in presence of ACOH, hydrolysis, then into that POCl3 in presence of pyridine, and finally we got the product over there. I think with this we have completed all the content point to point syllabus of Chiron approach. So tomorrow onward we are going to see the section number 2, which is a carbohydrate, and that detailed study we will see tomorrow. I think with this, let us stop today here. Have a nice day. Thank you.